Let's look at another example for testing a hypothesis on a population proportion. A study of sleepwalking, or nocturnal wandering, was described in Neurology magazine, and it included information that 29.2% of 19,136 American adults have sleepwalked. Would a reporter be justified in stating that fewer than 30% of adults have sleepwalked? Use a 0.05 significance level to test the claim that for the adult population, the proportion of those who have sleepwalked is less than 0.3. We need to check our requirements. For a proportion, we have 3 of them. The first one is, do we have a simple random sample? Now, this is not explicitly stated in the problem, but we're going to make that assumption. We do have a large N, but a large N doesn't always mean a simple random sample. We could have a very bad volunteer survey, but we'll make the assumption that we have a simple random sample. The second requirement is that we have a binomial distribution situation. So we have a fixed number of trials. N is 19,136. Each trial is independent. We have one of 2 outcomes. They sleepwalked or they didn't. And our probability is assumed to be the same, 0.3. So even though this 30% is the claim is our population proportion. This 29.2% is our sample proportion. We also are given that alpha is 0.05, and if p is 0.3, then q, which is 1 minus p, is 0.7. The 4 requirements of a binomial distribution are met, and then the third requirement is that n times p and n times q are greater than or equal to 5. So calculating this, n times p, n times q. And notice, since p is the smaller one here, if we multiply n times p, and that number is bigger than 5, then it is automatically true that n times q is greater than 5 because q is bigger than p. So 19,136 times 0.3, 5,740.8, and 19,136 times 0.7, just to show it, 13,395.2. Both of these are greater than or equal to 5. So our requirements are met. Step 1, we need to state the hypotheses and identify the claim. Always 2 hypotheses. We're dealing with a proportion, so our parameter that we'll use is a p. The thing that we're testing is the proportion of sleepwalkers is less than 0.3. So that 0.3 is the value that I need for the hypotheses. I want you to sit for a second and notice the similarities between the 2 hypotheses. The only thing I have left is to put the symbol in the middle for each of them. The null hypothesis is always equality. The alternative is the inequality. And to determine which inequality, we go back to the statement, fewer than 30% of adults, or, in the last sentence, the claim, proportion of those who have sleepwalked is less than 0.3. So proportion less than 0.3. And then the claim is our alternative. Since this is a less than, this also tells us it's a left-tailed test. And then we can move into calculating to compare for the test. 2, 3, and 4 are in the template. So I'll use Google this time just to be different. See that we can use either one of these. And so there's a lot of data in here from the last problem that I did in the template. That's okay. I need to change the alternative hypothesis to a less than, and this needs to be 0.3. So I'm trying to match my claim. P is less than 0.3. Significance level is 0.05. My N is 19,136, so it'll be really big. And the number of successes we don't have, but we do have the proportion of successes in the sample, 0.292, that 29.2% that's given to us. And notice when we do that, they give us a calculation for number of successes. That's okay. We have our critical z-value right here, negative 1.645. We have our test statistic, negative 2.415, and we have the p-value. We have our critical value and our test statistic, these two we would compare with each other, or we would compare the p-value with the significance level. So we're going to look at both of them. The critical value, negative 1.645. The test value, we sometimes call this test statistic. This is that test statistic for the sample proportion, negative 2.415. And so using these two for the traditional method, I'll put my critical value on here, negative 1.645. The test value, negative 2.415. Critical value, negative 1.645, gives us a rejection region. And notice that our test value is falling inside the rejection region, which means that we need to reject the null hypothesis. If we're using p-value method, just to compare the two methods and show you that they give us the same results, our p-value, according to the calculation, 0.00786, so 79, and then our alpha was 0.05. Which one is bigger? I'm looking at the second place from the decimal. I have a 0 in the p-value and I have a 5 in the alpha, so the alpha is going to be bigger since this p-value, which is a probability, is less than my alpha. The p-value is indicating that the null hypothesis is unlikely. The p-value is too small, so my null hypothesis is unlikely, which means I reject the null. The exact same conclusion that we got from the traditional method. So making the decision, reject the null hypothesis. And we can summarize our results. The alternative is our claim. Come back up to our hypotheses. We're rejecting the null. The alternative is our claim. And the alternative has enough evidence, meaning this test is enough evidence to support the claim. So there is enough evidence to support the claim that the proportion of people who have sleepwalked is less than 30%. Going back to the original statement of the problem, this is really saying that this 29.2%, although in general 29.2 might be sort of close to 30%, because this n is pretty large, the statistical method is showing that the 29.2% is actually not close enough to the 30% to indicate that proportions are equal or that the population proportion is greater than 30%. It's really supporting that the population proportion is lower than 30%. And that's how we come up with that conclusion.